Hello, class. It's time for our lecture on measuring pressure. This is part 2 of that. We went through all this. I should have jumped ahead, but let's see. We're almost there. This is where we left off. We had been looking at all these different, say like a bellow or a capsule or something like that, that would have some kind of displacement with pressure. And then we would measure that displacement with any of the devices that we learned how to measure displacement with, and that then we would get the pressure from. One of those mechanisms that displaced with pressure, one of those transducers, was the diaphragm. And there were two versions of that. We have the thin-walled diaphragm, which is what we see over here on the left. And we have the corrugated diaphragm, which is what we see over here on the right. So corrugated. That's what I'm moving the cursor here over, the corrugations. Now, just to compare these, the thin-walled, this would be better for short stroke, where the corrugated is better for long stroke. So essentially, if a short range is all we need, then the thin-walled is better for that. If we need a longer range, then the corrugated one is better. We get a high-frequency dynamic range, meaning, say our pressure is fluctuating at a high rate, then the thin-walled will work better for that. If it's a slower rate, but we want more output, then the corrugated would be better. So here we're going to have better frequency dynamic range, smaller output. Here we'll have poorer frequency dynamic range and a larger output. So on this side, we have a short rise time. It's going to respond quickly. Over here, we have a good static signal. It will move to that position and stay there. We are going to go through a number of equations related to the thin-walled. So we're going to assign a new homework assignment, and these equations that I'm going to go over here are going to be very important for being able to solve those. The book doesn't really cover this, but we're giving you good equations here for it. So the first thing, we need to be able to calculate the natural frequency. That is going to be equal to all of this over here. We have Young's modulus, the thickness of the diaphragm, we have this gravitational constant. So this isn't just 9.81 meters per second squared. It is 1 if we're in the SI system. This is essentially to make the units work out. Or it's 386 pounds mass times inch over pound times second squared if we're in the US customary foot-pound system. And down here, we have Poisson's ratio, we have the density of the diaphragm, and we have the radius of the diaphragm. So all of these are going to be for that diaphragm. So we calculate these, we can determine the natural frequency. And that one reason why you would want to determine the natural frequency is it sets the upper frequency range limit. So if our natural frequency is 1,000, it's going to be greater than 1,000. Say it's 1 gigahertz. Then we would be able to measure frequencies up to 1/3 of that. So part of the reason for that is if you are driving something at the same frequency that its natural frequency is, then you're just going to blow it apart. But by keeping it down lower like this, we get a nice even response, and there's no danger that we're going to blow the system up. Now, remember there were a lot of properties in there, all the modulus, the thickness, the radius, density, Poissons, all that. What you select for your diaphragm in terms of, so the material, the thickness, and the radius, that's going to affect the dynamic range. So if we increase, say we pick something with a higher modulus of elasticity, then we're going to get a higher natural frequency. That's going to increase our dynamic range. Could do the same thing with thickness, but say if we add a lot of thickness to it, we're creating more mass that has to move. So it's going to be slower. We're going to have a longer rise time. And maybe moving in the other direction if it was a really light construction so that we get a quick response time, then over time it's going to, well, anything is going to degrade over time. We're going to get drift, but if it's a much more delicate, just lighter construction, it might drift sooner, more. So thinking about all these properties, you can get the characteristics that you want to get for your sensor. Another important characteristic is that for these non-corrugated diaphragms, the deflection must be less than 1/3 of the thickness. So this is a key point. And then to determine the displacement, that would be equal to 3 times the change in pressure times 1 minus Poisson squared times the radius to the fourth, or 16 times Young's modulus times thickness cubed. So that Y max, that's the max elastic deformation at the center of an edge-supported circular diaphragm. So if you apply a certain pressure to it, has all these properties, then at the center where you have the most displacement, that's the displacement. What you'd get from calculating this is that displacement you would get there. And that must be less than 1/3 of the thickness. So again, this is going to be very helpful for you solving the new homework assignment. And this example will even help more. So the question here, or the problem statement, you are supposed to determine the natural frequency for a 316L stainless steel diaphragm. It is 5 millimeters in diameter with a thickness of 0.05 millimeters. So the natural frequency equation, that's what we'll start with. That's the one we just learned on the previous page. It's up here. And then, so this is just the problem statement here. If it's homework and you're not, so obviously you need some material properties, right? You need the Young's modulus. We have the thickness. We can determine this from the notes we have. We need Poissons. We need the density. So go and look those up for 316L stainless steel. And we would get these values. Or like Engineer's Toolbox or something like that. Some relatively reliable web page or one of your books, and you can get information like this there. So do that. And since we are in SI units, then our gravitational constant is going to be just 1 kilogram time meter over newtons times second squared. And then all we need to do is plug things in. So we're just plugging all this into this equation up here. So the Young's modulus, we've converted that to, what was that, gigapascals, so giga, then pascals to newtons over meter squared. And then here we had the thickness, which was 0.05 millimeters. So we move the decimal spot over 3 to be millimeters. We square it. We have that gravitational constant in there. We have 12 over 1 minus Poisson's, which we found is just 0.3. We square that. And then the density, I think we found it was 8 grams per cubic centimeter. You can convert that to kilograms per centimeter cubed. So here we just moved the decimal over 3 spots to the left. Boom, boom, boom. We're still going to have to do something with the centimeters. And then here we have that radius to the 4th. So since we have the diameter, we put that 5 millimeter diameter in meters divided by 2. So we get the radius, and then we quadruple it. So next step, we simplify everything or calculate what everything in the numerator is. The newtons, I guess, just cancel out there. We end up having 1. Oh, no, there's those 2 meters there. So those cancel out to be that, and the 2 seconds there, those come there. And a lot of this simplifies down to this. And then we need to convert those centimeters. So 100 centimeters per meter, and we need to cube that. And then this whole term here equals this. It's quadrupled. So calculate, simplify it down again. Numerator is still the same. And we get everything in the parentheses down to something. We take the square root of it, and we get this. So that says kilohertz there. It actually should be radians per second. We come to radians per second here. Using omega here, you know that it's radians per second. If there's an F, then it would be in hertz. So we get 762.8 radians per second. And since radians are equal to 2 pi, the frequency in hertz, we just divide this by 2 pi, and we get a frequency of 121.4 hertz. Now, the next part of this, so what is the max differential pressure that could be applied? So here you need to take your Y max equation. That was what we were given a few slides back. And then also this thing we said was important, that deflection must be less than T equals, or T divided by 3. So we're looking for the max differential pressure. So we rearrange this for pressure. We have this in Y max here. So we substitute in the T over 3. So this T comes to T fourth, this 3 brings us to 9. So this is going to be our equation for the maximum change in pressure. And we just got to plug things in, do that, and we end up getting 60.3 kilopascals. And just if you want to see what that is, the conversion from 1 psi, or 1 psi is 6.895 kilopascals. So this is 8,750 psi. That might be a little more familiar to you. So I wanted to just show a real world example. That example was kind of made up, getting somewhere close to this. I think for our resonant frequency, we had something like 121 kilohertz, something around that range. This one's 500 kilohertz. It tells you here that high frequency range it can go up to 170 kilohertz, which is approximately 1/3 of the resonant frequency. Then this particular one comes in different models, so you can get different PSIs. We had 8,750 PSI, so we were kind of between these models. And it's similar material. If we messed with radius and thickness and stuff like that, we could get to closer to these numbers, but we already are pretty close just after a first guess. Now the homework is going to be, I'll talk about that node in a minute. The homework is going to be I'm sorry, let me talk about that now. Then we'll talk about the homework. So this thing that's added on here just says combustion engine in-cylinder pressure varies at a frequency of up to 30 kilohertz. So this one goes up to 170 kilohertz. We have some pretty high pressures that can be measured. So we don't have the pressures for this, but we have the range, the upper end of the frequency range. It satisfies that. Actually, this one is meant for measuring combustion engine in-cylinder pressure. So obviously it's a good choice for that if that's what it's meant for. But just a little bit of information there. Now back onto the homework. That example we just did is very similar to what you're going to need to do in the homework. You're going to need to do it for a few different materials. And then the homework is also going to ask you to talk about, I think it asks you to compare the natural frequency and something else based on stiffness. And I think it says stiffness and mass. I don't remember exactly what the question asks you, but I do know it asks you to give some kind of a qualitative judgment of or comparison between the different ones it has you calculate for based on stiffness changes. And you might not readily see in that equation where stiffness is. So I want to give you a few equations for, so this would be for a diaphragm supported at the edge. In that case, the stiffness, or K, is equal to 192 times pi times the flexural rigidity times R over R squared. And then that flexural rigidity is equal to this. So if you substituted this in to here, and then you, so basically you would be inserting, you want to get the K into your equation for natural frequency, right? So you're going to have this is equal to all this times this. You might need to move some things over, but there should be something over here where you can take that out of the equation for natural frequency and get K in there. So you'll be able to see more where the stiffness is in that equation and how changing it is going to affect your output. So hopefully that's helpful to you. That isn't the only way you can get there. If you like math and you want to be precise, you really want to see how it all works out, that's a good way. There are also, you could say, some similarities between just a spring mass system. If you know what the relationship between stiffness and mass and the natural frequency is, you can probably make a fair qualitative assessment of how that stiffness is going to affect the natural frequency. So there are a few ways you could go about solving that. So this slide here, we're talking about the time response of a pressure transducer of a diaphragm. So we have this diaphragm sensor. We have pressure on one side, reference pressure on the other side. Changes in pressure means this is going to move. But the membrane, it has inertia, and there's a motion requirement there. So those things limit the dynamic capabilities. We're going to have the output lagging behind the actual measuring change. So just be aware that occurs. There's a response, a time response to it. And then here we have multiple choice question for you. Question is, what is the best way to generate an analog voltage signal from a traditional Bourdon tube? We have 4 choices here. You want to pause it and think about it, do that. I will I'll just go ahead and answer since you can pause it. So first we have a choice between A and B. So they're both a powered rotational potentiometer. One is a standard DAC, one is a high impedance DAC. If you remember remember a potentiometer is essentially a variable voltage divider, and you need to have a high impedance input. That's one of the things we said about that potentiometer way back. If you remember doing the problems where you had that load resistance there, a greater load resistance is going to result in less error. So high impedance DAC would be a good choice between those two. And then we have C and D also. And you see the answer here. I'm just walking you through the reasoning. But an RVDT would be a good, so rotary variable differential transformer would be a good choice as well. So the best answer here would be B or C, because both B or C are great ways that you can measure that displacement. That's it for this. Talk to you later.